Hello, this is Valentin Bura, and I have proved previously the collapse of the polynomial hierarchy. A great result in itself. That particular proof is on arXiv. It's a paper. The paper is called Positive 1 in 3 set admits a non-trivial kernel. It is on arXiv. You may find it under my name. An awesome result, hence the poetic style of the paper, as nobody thought that the polynomial hierarchy would indeed collapse. So for that paper, be prepared to be shocked a little bit. Okay? Right now, I'm going to run you through my proposed proof for the Riemann hypothesis. Yes, the Riemann hypothesis, probably the greatest unsolved problem in mathematics in the last 200 years or so. So, yeah, bear with me on this one. Thank you. Let's get to work. The Riemann hypothesis. A problem proposed by Bernard Riemann, as the name suggests, of course, a very, very long time ago. Arguably the most important problem in mathematics today, if I'm not mistaken. The status of this conjecture is open. Srinivasa Ramanujan has done a lot of work, yes, of course, Ramanujan and Hardy, yes, at Cambridge, beginning of the 20th century. I think Paul Erdős did some work on it. Erdős was a keen number theorist. What we are going to focus on in this approach is a paper by Robin, published in 1982, I think, which sort of elaborates a little bit on the results of Srinivasa Ramanujan. A matter of notation, we write very simply the following identity. Phi of n equals e to the gamma n log n. So, phi of n is e to the gamma n double logarithm of n. Phi is a function, of course, it's a function on the positive integers. E in this context is the base of the natural logarithm. Gamma is Euler's constant. We will take it as defined by Robin. I'm not going to explicitly write it here. This is not the course in mathematical analysis as such. The proof itself does not make much use of mathematical analysis. It's basically a combinatorics proof. Technically speaking, I work in computer science and in combinatorics and optimization. Phi of n here for a complex expression. The paper makes use of this technique, well, it is syntactic sugar really, to simplify things. So we write symbolically phi of n for this particular expression, e to the gamma n double logarithm of n. If you know about Łukasiewicz and Łukasiewicz logic, you can see it's kind of similar. So we make use of that in order to simplify notation a little bit. I hope you will enjoy this in the paper itself. We also write sigma n to denote the sum of divisors function. So sigma n, that's standard notation in number theory, elementary number theory, the sum of divisors function. Example. So, okay, sigma 4 equals 7. This is because 1 plus 2 plus 4 equals 7. So 1 divides 4, 2 divides 4, and 4 divides 4. So therefore, sigma 4 equals 7, 1, 2, and 4 being the divisors of 4. Sigma 5 equals 6. This is because 1 plus 5 equals 6. Yes, 5 is a prime number. Sigma 6 equals 12 similarly. It is, as the name implies, the sum of all divisors of the positive integer n. So that's what sigma n is. Notice that this is fluctuating actually. It's not strictly increasing or, okay, strictly decreasing, but it's fluctuating, so it can take very high values and then come to a low when we reach a prime number, and then it can go up again. Very neat way of making an account of the prime numbers in the positive integers. Robin's criterion. 1982, Robin proves that this problem, this conjecture, the Riemann hypothesis, holds if and only if sigma n is less than phi n for a finite number of values of the positive integer variable n. To restate this, if sigma n is greater than phi n for infinitely many n, then the Riemann hypothesis fails. But I've given you the hold condition here. So sigma n must be less than phi n for a finite number of values of the positive integer variable n. We show here this is in fact the case, that sigma n is indeed less than phi n for only a finite number of values of the variable n. There are a bunch of values for sigma that do not verify the claim. They start at 2 and they finish at 5040. Just a handful. These are the cases that do not verify the claim. A key observation here is that all of the previously stated values, the values that do not verify Robin's criterion, are a combination of the following form. It's a product, so it's 2 to the a times 3 to the b times 5 to the c times 7 to the d, for values of a, b, c, d that are bounded above and in fact extremely small. So we prove here Robin's criterion fails for positive integers that are necessarily smaller than the following threshold. And it's, okay, 2 to the 5 times 3 to the 3 times 5 to the 3 times 7 to the 2. Okay, this is probably higher than necessary. A computer search shows that the numbers stated before, the numbers that begin at 2 and end at 5040, are the only ones that fail Robin's criterion. This is a technical condition, and this is the bound. We prove in our paper that any positive integer that is greater than this threshold must necessarily satisfy Robin's criteria. Now, another key observation. When we think about the natural numbers or the positive integers, we think about counting, right? 1, 2, 3, 4. So it's the natural order induced by counting or by the successor operation that maps n to its successor, n plus 1. That's what we have in mind when we think about the natural order on the integers. And pictorially speaking, this is what happens if we compare sigma to phi using the natural order on the integers. This is the picture. So we can see a function, it's clearly growing, but it's fluctuating. And really nobody knows, or nobody has really proved Robin's criterion in fact holds for all of the numbers above a certain threshold. Hence, the Riemann hypothesis is open. In this particular case, in this particular instance, we must think outside the box. We must find a different order on the positive integer numbers. The natural order on the integers is a little bit misleading here. We are going to use a result that most of us are familiar with, the unique factorization theorem. This says that every integer greater than 1 is either a prime number itself, or it can be expressed as a product of prime numbers, and this representation is unique. Okay, so this is a technical requirement, a very fortunate theorem, and this induces a special order on the positive integers, on the natural numbers. This order is a partial order on the positive integers induced by each integer's prime factorization. And the order looks like that. It is a partial order. And it's very, very good news. Extremely good news, because this allows for a mathematical induction on a thing called structure of the integer factorization. So we can basically do an induction on this partial order. Really, that's not a new concept that as such, because I've met that before personally in model logic, in Creswell and Hughes. In logic, yes, it's very common in logic, induction on structure, basically. But I'm applying it to the factorization of the positive integers. That's all there is to this, if we want to keep it in a nutshell. Pretty much. That's all there is to this. If you have some level of expertise in elementary number theory, you will see this is pretty much correct. You will understand where this is going. There's no need for elliptic curves and Drew Wiles kind of stuff. This is really just elementary number theory and case analysis. It's combinatorics, really. If you know a little bit about elementary number theory, you will see where this is going. You will see, otherwise it would be just like David Beckham missing a penalty kick, which didn't really happen very often. So yeah, it's like that a lot. Okay, so you may want to check my 2 papers. Well, I have more than 2 papers. I've contributed a lot in the past. So the 2 papers, the first one about the collapse of the polynomial hierarchy. And this paper is called On Sum of Divisor and Robin's Theorem. It is on Academia, it is on ResearchGate, it is on my personal website, valentinbura.online. And a few acknowledgements. I need to thank Noam Greenberg, my academic advisor in Wellington. Noam is an excellent mathematician. I've learned a lot from him. I can say that we've collaborated well. And I need to thank the people at my mother's place of work in Subiaco, as my mother has financed most of my research in the past and my graduate studies. Thank you very much for your attention on this.